Good day everyone, and welcome to week 5 of the differential equations course. Today we're going to learn some theory of second order differential equations. So here is the plan for today. Please note that it is very important that you review certain concepts from linear algebra in order to understand today's lecture. So if you don't remember what a vector space is, please pause the lecture and review this concept. Okay, so let's look at what we've learned so far about first order ordinary differential equations. So here is the general form of a first order ordinary differential equation. So the left hand side is the derivative of the unknown function, and the right hand side is some expression in the independent variable and in the unknown function. Well, here is the most general form of a linear first order ordinary differential equation. So strictly speaking, it is not exactly in that form, but you can of course rewrite it as y prime equals minus p of t y plus q of t, and then the right hand side becomes f of ty. Well, a linear first order differential equation may or may not have constant coefficients. So, and if it has constant coefficients, if p of t here and q of t are not functions of t but rather just some fixed numbers, then we're going to find its general solution. The reason is because it's going to help us to approach second order differential equations. So the first step to solve any first order linear differential equation is to find the integrating factor. So then we multiply our equation by the integrating factor, and then the left hand side becomes the derivative of the product of the unknown function and the integrating factor, and then we just integrate it, and then we solve it for y, and here is the final answer. Well, the reason I did that is because note that this part, the constant times something, has this form where it involves the exponential function. So this is very important, that here we have the exponential function of minus at, and we are going to use that for second order differential equations too. Well, now the most general form of a second order ordinary differential equation is where the left hand side is the second derivative of the unknown function, and the right hand side is a certain function of 3 variables now, and we substitute t, y, and y prime as these 3 variables. And so I don't know, for example, so imagine that you have a function of 3 variables, say t, y, z, that looks like t square minus cosine y plus e to the power y minus z. So then, letting z to be y prime, we construct the second order differential equation y double prime equals t square minus cosine y plus e to the power y minus y prime. So this is a second order ordinary differential equation. Well, but if it is a linear second order differential equation, then it should be linear in y prime, and y double prime, but it does not have to be linear in t. Well, a new word. So if the right hand side of a second order linear differential equation is 0, so suppose that this part is just 0, then this equation is called homogeneous. Now let's look at equation 1 again. So suppose that this is not homogeneous. Suppose that you have something like y double prime plus ty prime plus cosine t times y equals no ln t. This is a second order linear differential equation, non-homogeneous. But then we can construct an associated homogeneous equation by just replacing the right hand side with 0. Here are a few examples. This is a linear homogeneous equation with constant coefficients. It's called a harmonic oscillator. This is Newton's law of universal gravitation. This is also a second order differential equation, but notice that it is non-linear. So here t is the independent variable and x is the dependent variable, is the unknown function. So, and the unknown function is x of t. So notice that this is nonlinear. It is autonomous because t does not appear in the right hand side explicitly, and it is second order because the highest derivative is the second derivative. Okay, and this is an equation of a pendulum. It is also nonlinear. So here theta is the unknown function, right? So theta is the unknown function. Theta of t is the unknown function, and g and l are parameters. So they represent g is the acceleration due to gravity, and l is the length of the thread of the pendulum. But they, for every specific pendulum, they are just some specific constants. And theta is the unknown function. So this differential equation tells us that the second derivative of the unknown function is proportional to sine of the unknown function.